Hello students, this is the lesson on derivative of inverse trigonometric functions. In chapter 5 we have completed, I have uploaded the lessons on continuity, then differentiation of composite function using chain rule, then differentiation of implicit functions, that is implicit differentiation. This is a third one actually, that is the derivative of inverse trigonometric functions. As you know, in the second chapter we have studied inverse trigonometric functions. There are 6: sine inverse x, cos inverse x, etc. And we have derived the formula for sine x, cos x, etc. last year. Differentiation of sine x, differentiation of cos x. Now this year once again we have to derive 6 results actually. Sine inverse x, what is the differentiation of sine inverse x, what is the differentiation of cos inverse x, etc. Therefore in the beginning let me first show you the proof of derivation of this formula, that is derivation of inverse trigonometric functions. Then using this formula we can find the derivative of any given inverse trigonometric functions, even composite function. So let us begin. First one is derivative of sine inverse x. So the formula is this: d by dx of sine inverse x is 1 upon square root of 1 minus x square. So this formula you have to remember. Let us first prove. Let y equal to sine inverse x. Then by definition x will be equal to sine y. Now we have to differentiate. Differentiating both sides with respect to x. Left side you get 1 because d by dx of x is 1, equal to right side it is cos y but into dy by dx, because differentiation of sine y is cos y. Because we are differentiating with respect to x, we have to use chain rule. So it is cos y into dy by dx. Therefore you can say dy by dx equal to 1 upon cos y, cross multiply. But now this equal to 1 upon cos y can be written as square root of 1 minus sine square y, but sine square y is x. Therefore we are getting the formula 1 upon square root of 1 minus x square. So this is the derivation. But you have to remember one thing: dy by dx exists only for x belonging to minus 1 to 1. You know sine inverse x is defined in the closed interval minus 1 to plus 1. But here x is in the open interval because x cannot take the value of plus 1 and minus 1. 1 minus x square becomes 0 and 1 minus x square is in the denominator under the square root. So we have to exclude minus 1 and plus 1. Let us proceed. Second one is cos inverse x. So the formula is d by dx of cos inverse x is minus 1 by square root of 1 minus x square. So the formula is same as sine inverse x, change is only in sign. So this you have to remember. So proof: let y equal to cos inverse x, then x will be equal to cos y. Once again differentiating both sides with respect to x. So d by dx of x is 1, equal to differentiation of cos y is minus sine y into dy by dx because of the chain rule. Now therefore dy by dx will be equal to minus 1 upon sine y. Once again minus 1 upon sine y can be written as square root of 1 minus cos square y, and substitute cos y equal to x, you get minus 1 upon square root of 1 minus x square. Here also same thing, it exists only for minus 1 to 1. Same reason, x cannot take minus 1 and plus 1, therefore you have to exclude it. Therefore x belongs to the open interval minus 1 to 1. Whereas for cos inverse x, x can be minus 1 and plus 1 also. So this is the care we have to take whenever we differentiate. This is the second one. Let us proceed. The third one is differentiation of tan inverse x, that is d by dx of tan inverse x is 1 upon 1 plus x square. So this is the formula. Let us prove this first. Let y equal to tan inverse x, therefore x will be equal to tan y. Now differentiate both sides with respect to x. So left side will be 1, d by dx of x is 1, that is equal to differentiation of tan y is secant square y, but we have to multiply by dy by dx. Now once again dy by dx will be equal to 1 upon secant square y, but now secant square y can be written as 1 upon 1 plus tan square y, and tan y is x, therefore substitute. So this is 1 upon 1 plus x square. So here you can see dy by dx exists for all values of x, real value. Therefore you can understand this one. It is existing for all values, no condition. So this is the proof. So three trigonometric formulas we have derived, that is inverse sine, inverse cos and inverse tan. So we have to find the derivative for the remaining three also. Let us proceed. Next, the derivative of inverse trigonometric function cot inverse x. So formula is, it is minus 1 by 1 plus x square. You can see the relation. Of course later I will conclude and show you how to remember this 6 formula. Let us prove first. Let y equal to cot inverse x, then x equal to cot y. As before, differentiate both sides with respect to x. Left side 1, d by dx of x is 1. Right side you get, what is the differentiation of cot y? It is minus cosecant square y into dy by dx. Therefore, dy by dx will be equal to minus 1 by cosecant square y. So here once again cosecant square y can be written as 1 plus cot square y. So then substitute cot square y equal to x square. Therefore the formula is minus 1 by 1 plus x square. Here also dy by dx is defined for all values of x, because 1 plus x square in the denominator is defined for all values of x. So this is the proof. Let us continue and prove the remaining two also. Next one is cosecant inverse x. So d by dx of cosecant inverse x is minus 1 upon x into square root of x square minus 1. So this is the formula. Proof. All the 6 proofs are similar. Y equal to cosecant inverse x. Therefore x equal to cosecant y. Differentiate both sides with respect to x. Left side 1, right side differentiation of cosecant y is minus cosecant y cot y into dy by dx. Therefore dy by dx will be equal to minus 1 upon cosecant y cot y. Substitute. So first one, cosecant y is x. Cot y can be written as square root of cosecant square y minus 1, and cosecant square y is x square. Therefore it is minus 1 by x into square root of x square minus 1. Therefore dy by dx here also this exists only for r minus 1 to 1, because here also same problem. You cannot take minus 1 and plus 1. So this is the condition. This type of condition you have to remember, because sometimes in examination they ask, see same question, for what value of x d by dx of cosecant inverse exist, like that. And the last one is secant inverse x. Now you can guess what is the formula. D by dx of secant inverse x is same as actually d by dx of cosecant inverse x only, but there is a change in sign. So it is 1 upon x into square root of x square minus 1. Let us prove. Let y equal to secant inverse x, then x equal to secant y. Differentiate both sides. So left side 1, right side differentiation of secant y is secant y into tan y into dy by dx. Once again dy by dx will be equal to 1 by secant y tan y. Now secant y tan y you have to replace by x. Therefore this is 1 upon x into square root of x square minus 1. Tan y is square root of secant square y minus 1. So it is x square minus 1. Once again you have to note this one. This is defined for r minus 1 to 1 open interval. So this is the proof. So totally there are 6 derivatives for 6 inverse trigonometric functions. Now, let me show you how to remember this 6 in a simple way. See, the first one is d by dx of sine inverse x, 1 by square root of 1 minus x square. D by dx of cos inverse x is minus 1 by square root of 1 minus x square. So change in sign only. Then d by dx of tan inverse x is 1 by 1 plus x square, and d by dx of cosecant inverse x is minus 1 by x into square root of x square minus 1. Same thing, secant inverse x is 1 by x into square root of x square minus 1, and cot inverse x is minus 1 by 1 plus x square. How to remember? So sometimes it will be confusing. So there is a connection. Let me show you. Look at this one, d by dx of sine inverse x. It is 1 upon square root of 1 minus x square. One type of formula. Look at this third one, d by dx of tan inverse x. It is 1 by 1 plus x square. Formula is different. And one more is d by dx of secant inverse x. Formula is 1 by x into square root of x square minus 1. All these three formula, it is plus. Now look at the remaining cos inverse x. It is minus 1 by square root of 1 minus x square. Then here also it is minus for cosecant inverse x, and for cot also it is minus. Therefore you can remember like this. Whenever it is c, the function begins with c, it is negative. Cos c negative, cosecant c negative, cot c negative. This is one thing. Second one is for all non-c functions, that is sine, then tan and secant, it is positive. One thing. Second one is formula for sine and cos, that is sine inverse x and cos inverse x, same. Formula for tan and cot, same. Formula for cosecant and secant, same. Only change in sign. So this you can remember. Now let us work out one example in the beginning. Find dy by dx if y equal to tan inverse of 2x by 1 minus x square. So here, in fact, you can also do this problem by substitution method, that is chain rule, but that will be very lengthy. If you use a trigonometric, inverse trigonometric substitution, problem will be simple. So y equal to tan inverse of 2x by 1 minus x square. Now what you have to do is put x equal to tan theta. Now we get y will be equal to tan inverse of 2 tan theta by 1 minus tan square theta. But you know this one, tan 2 theta is 2 tan theta by 1 minus tan square theta. Therefore you can write this as tan 2 theta. Therefore tan inverse of tan 2 theta, this will be equal to 2 theta, but theta is now tan inverse x. Tan inverse x. Therefore now it is very easy. So dy by dx will be equal to 2 into d by dx of tan inverse x. So which is 2 by 1 plus x square. So this is the technique you have to remember. So this is one illustrative example. Now let us work out the exercise problem 5.3. I have taken almost all examples because this exercise contains only a few examples. Let us do it. First question is 5.3, ninth question, because this exercise contains both implicit differentiation and this inverse trigonometric differentiation. So first one is find dy by dx if y equal to sine inverse of 2x by 1 plus x square. Now you can guess what is the substitution. So it is not chain rule now. Say consider y equal to sine inverse 2x by 1 plus x square. Put x equal to tan theta once again. Then y will be equal to sine inverse of 2 tan theta by 1 plus tan square theta. Now if you remember, last year you have studied this one. Sine 2 theta is 2 tan theta by 1 plus tan square theta. Therefore you can write this as sine inverse of sine 2 theta. So this will be equal to 2 theta. But now what is theta? Theta is 2 tan inverse x. As before, dy by dx will be equal to 2 into d by dx of tan inverse x. So answer is once again 2 by 1 plus x square. This is the ninth question. Next, question number 10. Find dy by dx if y equal to tan inverse of 3x minus x cube by 1 minus 3x square. I think now you can guess what is the substitution, and don't do this type of question by chain rule. You have to do by substitution so that problem becomes simple. X equal to, now put tan theta once again, y will be equal to tan inverse of 3 tan theta minus tan cube theta divided by 1 minus 3 tan square theta. But you know this formula, tan 3 theta is 3 tan theta minus tan cube theta divided by 1 minus 3 tan square theta. Therefore, the given function becomes now tan inverse of tan 3 theta. Therefore, this will be 3 theta. So, dy by dx now becomes 3 into d by dx of tan inverse x. So, it is 3 by 1 plus x square. So, this is the 10th example in the exercise. Let us proceed. 11th question. Find dy by dx if y equal to cos inverse of 1 minus x square by 1 plus x square. Now, definitely you can guess what is the substitution. So, y equal to given cos inverse of 1 minus x square by 1 plus x square. Put x equal to tan theta. Therefore, y will be equal to cos inverse of 1 minus tan square theta by 1 plus tan square theta. But you know this formula, cos 2 theta is 1 minus tan square theta by 1 plus tan square theta. Last year you have studied this. Therefore, you have to remember all the formula. Cos inverse cos 2 theta. Therefore, this is once again 2 theta, but theta is once again 2 tan inverse x. Therefore, differentiation will be dy by dx will be equal to 2 into d by dx of tan inverse x. So, 2 by 1 plus x square. Now, there is a small twist you can give to this problem. Instead of cos inverse x, suppose it is sin inverse x, then also you can do. Here what happens is sin inverse of cos 2x, and then cos 2x can be written as sin of pi by 2 minus 2 theta. So, there is only change. That is also possible. So, this is example 11. Example 12. Find dy by dx if y equal to sin inverse of, see, same thing, 1 minus x square by 1 plus x square. So, what is the difference? See, earlier it was cos inverse. Here it is sin inverse, but inside the bracket it is same, 1 minus x square by 1 plus x square. Let me show you. See, y equal to sin inverse of 1 minus x square by 1 plus x square. This is the given function. Substitution is same. Put x equal to tan theta. Then y will be equal to, see here, 1 minus tan square theta by 1 plus tan square theta. But this you know, this is cos 2 theta. In the previous example, you have seen this one. Therefore, here you see sin inverse of cos 2 theta. But now how to do it? Sin inverse of cos 2 theta. Therefore, here the trick is sin inverse of cos 2 theta can be written as sin of pi by 2 minus 2 theta. Now, sin inverse of sin becomes identity function. So, it is pi by 2 minus 2 theta. This is the trick. So, this will be equal to pi by 2 minus 2, then tan inverse x. This you can differentiate because pi by 2 is a constant after all. Therefore, dy by dx will be equal to minus 2 tan inverse x by d by dx of tan inverse x. That is, pi by 2 becomes 0, differentiation. Minus 2 constant you can take out, d by dx of tan inverse x. So, this will be equal to minus 2 by 1 plus x square. This is the important thing which you have to note. Now, same thing you can see, a problem can be y equal to cos inverse of 2x by 1 plus x square. Same thing. So, next example 13. Find dy by dx if y equal to cos inverse of 2x by 1 plus x square. Exactly same. So, this can, even you can do it as homework. Let me show you. So, here put x equal to tan theta. Problem is same. Y will be equal to cos inverse of 2 tan theta by 1 plus x square. But you know that this is sin 2 theta. This is sin 2 theta. So, cos inverse of sin 2 theta. Here also same thing. Cos 2 theta should be written in terms of, sin 2 theta should be written in terms of cos 2 theta. So, this is cos of pi by 2 minus 2 theta, complementary ratio. So remaining things are same. 2 tan inverse pi by 2 minus 2 tan inverse x. Therefore this you have to differentiate. Once again, pi by 2 is constant. When you differentiate, it becomes 0. Therefore dy by dx will be equal to minus 2 constant comes up, then d by dx of tan inverse x. I have not shown pi by 2 0. That is the thing. Differentiation of pi by 2 constant 0 I have not shown. So this will be equal to minus 2 by 1 plus x square. So this is the way you have to tackle the problem. Example 14. See, if y equal to sine inverse of 2x into square root of 1 minus x square, what is dy by dx? Here you see the substitution changes. So in all the previous question it was substitution tan theta. Here what you have to do is put x equal to sine theta. Even cos theta also possible, but I take x equal to sine theta. Now you see what happens is y will be equal to sine inverse of 2 sine theta into square root of 1 minus sine square theta. This can be written, now you know this rule. Sine 2 theta is 2 sine theta into square root of 1 minus sine square theta, because 1 minus sine square theta is cos square theta, cos theta. Therefore this is sine 2 theta. Therefore this will be equal to 2 sine inverse x. Therefore d by dx of this will be equal to d by dx of this divided by 1 plus 2 divided by square root of 1 minus x square. So this is the result. Thank you for watching this lesson. Please subscribe and share if you have not subscribed my channel. As I told you already, I will be uploading all the lessons of second PUC. But you have to excuse me because it takes time for me to prepare the lesson and upload. I have already started from first chapter, but because of the time required for uploading, sometimes it will be delayed. Some students already expressed, sir, you are skipping some of the lessons and going. It is not skipping actually. I have to prepare the lesson and then I have to record, then I have to upload. Therefore it takes time. Please note, I will be uploading all the lessons from chapter number 1 relations functions to chapter number 13, that is probability. I am preparing LPP and probability lessons and 3D lessons also, all the lessons. Even in integration I have started uploading the lessons because some students asked me, please upload the lessons on integration also. Therefore I am uploading simultaneously all types of lessons. So please watch the lessons so that it will be an encouragement for me, so that I can do it still better. And simultaneously I have also started uploading the lessons on CET, because some students requested me, sir, this is the high time for us to prepare for CET also. Please upload the lessons on CET. Therefore I am uploading the lessons on CET also. Already I have uploaded many lessons. Please watch those things also. Let us meet in the next lesson with now it's the inverse trigonometric function and its substitution method is over. Then I have to take log and logarithmic differentiation. Then I have to take second order derivative also. All these lessons definitely I will be uploading. Please watch all the lessons and get the benefit. Let us meet in the next lesson. Till then, bye. Take care.